400 hard drives based on them.
Yeesh.
It's pretty fun and entertaining.
So, okay, good morning. Want to welcome each and every one of you to our spring 2023 AI at AU forum. Today, we're going to have Dr. Anh Nguyen talking to us about trustworthy and explainable artificial intelligence. So join me in welcoming Dr. Nguyen.
Hello, everyone. Let me check if the online people can hear me before we start. You guys hear me? Anyone online?
Yes.
Yes.
Yeah, they can hear you.
I do not hear them.
So Pan, he said yes.
Okay.
Go ahead and
Can they speak?
Yeah.
But I do not hear them. So
They just type it in.
Okay, they'll type it in.
So it's
You'll
one way,
probably hear it from here.
Okay, so for those who do not know me, I see a few new faces here. So my name is Anh. I'm originally from Vietnam. I came to the US in 2011. Before that, I was software engineer at a few places, including Robert Bosch, where I lead some building the software that makes their system interact with humans. So I was in this space for some time. At the software side, I came to the US. I was stunned by the deep learning at that time. So I started my career around 13 or 14 in AI, almost 10 years now. And the journey has been incredible. I want to share with you two aspects of AI that I'm really, really excited about. It's trustworthy and explainable. Okay, so if you are a fan of sci-fi movie, you might have seen a couple. For example, iRobot. The typical motive is like AIs or robots. In this talk, robots and AIs are interchangeable. They are slaves of human, right? And then at some point, they will make a plan to take over the planet. And Will Smith is the agent there who's trying to destroy the plan. Singularity is another hypothesis where we start to see like very slow AI development until at one point it's like a log curve, exponentially growing, where you cannot control the intelligence of it anymore, beyond human. And so will this happen, right? Okay, let's see. Many philosophy researchers, professors, physicists around the world, from Cambridge to MIT, they conjecture this hypothesis: killer robots could enslave humanity before eventually wiping us out. So do you believe in this? I would laugh at this the first time I see it.
I mean, only if you're
Who believes in this strongly, wholeheartedly? Okay, good. But at least you have to ask some question. Wiping us out? I mean, wiping what out? Right. So okay, let's put that's a bit into the futures. But killer robots and could enslave? Why? Why could? So there's a possibility that the robots will not enslave humans, right? And there's a possibility that robots will not killing us, right? So let's see. But wait a second. Are we already not slaves to robots? At this moment. So if you use a smartwatch, congratulations, you're wearing this shiny digital handcuffs. That allow the AIs to do things to you like, hey, take a minute to breathe right now. No, your heart rate is not going well because it seems like you're idle. Now stand up, guys. Move a little for 1 minute. Okay, so who's the slave to who? Okay, so let's say you don't have a smartwatch like me, that's fine, but you must have a phone, right? So what happens? This is usually the scene I walk around the campus, and unfortunately I see this a lot. Even on the hallway here, in this building. Very sad scene. Why? Because we are open this phone and then chances you are Googling and you hit this one true answer problem. For many, many years, Google was invented before I started college, so I did not have this tool before. It was around 2004 when I first learned how to Google. It was the first time it came up. But for almost 20 years, it has been manufacturing the way we see the world. All the things you call facts are just the evidence, the statements put out there by Google. They form how you shape how you think. So now think again, who's slaves to who, right? You or the AI? If you, on the phone, you will open Facebook, probably TikTok, and whatsoever. The chances, if you have seen recently, people are having this conspiracy theory where many people think that actually Facebook and these phones are hearing on you, right? Because every time you search something on Google, you open Facebook, suddenly the ad appears there. You talk to your wife about hey, let me change the diaper for our kids because the previous one does not work. However, suddenly the next day you open Facebook, it appears right there. So it caused a huge, it happened to me as well. And when I look up the internet, I found out, oh, there's no way this can happen. Because you need an extremely high bandwidth to listen to you constantly. And also the AI needs to basically extract the information from the hours of you talking in order to just send you a single ad. Actually, it does not need to. That's the whole point. It's crazy. However, it can predict very, very well exactly what you will do next and show you the right ads so well that you think it's hearing on you. That's the whole point. We are living in this bubble where AI is controlling us entirely. From what you see on Google, you think are facts, what you see on your social networks, and what you will buy next, right? So now, part of human is reproduction. You need to find your mates, partners, right, to expand the population, right? Even AI is controlling who you should reproduce with. Isn't that crazy? And okay, you have some successful reproduction, okay? But then the targets and then these online shops actually know whether you'll get pregnant before your dad will figure out. Happened to a teenager. It is target incident. So Facebook, still to these days, many people think that Facebook are hearing on you, but let me tell you, no, they don't need to, because they can actually predict what you'll do next already. They do not need to listen on you. And what else? What else? So if you walk on the street, chances you are captured by some CCTV, and then chances that AI is actually processing you and then comparing you with some database, and the police will use this the Clearview AI to tell whether you are suspect or not, and maybe go after you. Okay, so if you go to the jail because the AI says so, okay, then the court, the judge actually use AI to predict where the chances, what kind of sentence they would put on you, 5 years, 7 years, or whatsoever, predicting the chance of that you will re-offend if you committed a crime before. And then, of course, this driverless taxi is a reality already. You don't need to wait for L5. Self-driverless car, driverless cars. It's already running in San Francisco. They are picking up people. And so far, no major accidents have been reported. A few minor accidents, like the car is stopping a bit too fast, but actually it's a reality already. Not Uber, it's driverless Uber. Okay, so the entire bubble now is AI. the could, you could remove it. The robots actually already enslave humanity. Already, right now. How about killer? Are they killing us? Right? What's wrong if I go to Facebook? Who's gonna kill me, right? Actually, no. So the research has shown that from 5,000 people study. So if you use social media more, actually that correlates more with your depression, mental, physical problems. And 64% of people who join extremist group on Facebook did so because algorithm actually steer them into being extremist. This is into the Facebook report. And you must watch the social dilemma movies, this Netflix documentary about social media. It's crazy. How are they gonna kill us in different ways? Maybe not mentally, but physically they could also kill you. Apple Maps, they are notorious for sending motorists lost, stranded in the desert in Australia. And Tesla cars, just within 2 years ago, many accidents that which resulted in fatal incidents. People, in this case, two guys in the front seat, they decided for a moment that, oh, this car can drive itself, and then they jump into the back seat, and then I don't know what to do. And then when the car crashed and then killed the two guys who were found in the back seat of the Tesla. Okay, so people will think that driverless industry is now taking humanity, right? It's taking our jobs. You would think so. However, if you try the latest Tesla, this is SSD9, the latest is 11, so around 18 months ago. But at this point, it still can constantly misclassify the moons into yellow lights and keep running at a low speed because it thinks the moon here is a traffic light. But, however, it has actually many other problems like misrecognizing the roads, the lanes, one-way streets, and so on. It takes over the bus lane and many other things. So that's why you need trustworthy and explainable AI. So let's together build AIs that are accurate in edge cases and also common cases. So the trustworthy research, sometimes it's called trustworthy, but also robust AI. The reason it's the robust is because they want the AIs to perform similarly well, both in common cases and also when you change the case a little bit, move it to a slightly different, it still performs similarly well. So in accurate cases, because called robust. The trustworthy and robust in this topic are interchangeable. Or maybe also let's build AIs that can maximize human and AI team accuracy, because it seems like we are slaves to the AI now. There's no way you can get out of this bubble. There's probably no way you can get rid of AI. So probably we need to work with them. So how do you build AIs that you can work with, maximize both accuracy? And also, how can you build AIs that understand, that humans can understand their decision-making process, and also humans can debug this AI? Right. So let's talk about the first one. I want to build AIs that are robust or trustworthy, basically accurate in edge cases. So the typical setup of AI is like you first gather a lot of data, a million images here, and you train, for example, a school bus detector, right? The image classifier, typically it will give you very high accuracy if you give it like IID, the normal cases here. It will tell you this is a school bus, 100%, so fine. Everything works in a sandbox. However, they are actually quite brittle. If you just take this school bus out, put it in a 3D render and rotate it a little bit, you can find angles that cause the state of the art here, Google Inception Network, to misclassify into something else entirely. Not a school bus, not a school bus. No, none of these are school bus according to Google at the time of 2019. However, Google thinks they are chain, scabbard, forklift, and so on. we find some very also other very interesting patterns. For example, if you just take a shot at the slide and the side of the car, typically this network will think that this is a vacuum cleaner. And if you put it upside down, it will think this is a shopping basket. All of these 4 images. So there is some common failure pattern here, which we are not able to handle. We do not understand. We cannot explain their behaviors, and they are not trustworthy. I released this. We released this demo here that the students, if you are interested, you can try this by yourself to figure out. It's very simple. It's in Python. You can try and see this huge problem. Okay, so the current status is AI are most of the time accurate in normal cases, but in edge cases, you can safely say they are not. Okay, they are not accurate. Because if they're accurate, then you can use it everywhere. Okay, so how about human AI teams? What if you have to make very high-stake decision? What can you do? Right. So in this case, if high-stake decision, we want to build AIs that maximize our interaction, our team accuracy. Because when you put humans in a downstream task or the human AI in a downstream task, we need to maximize the accuracy. In many of these cases where transportation, finance, military, legal, or medical, we need this relationship to achieve high accuracy. So DARPA in 2016 released this program called Explainable AI, and it ended in 2021. 5 years where they proposed to change the paradigm from black box AI to this explainable AI. It says that first, usually the training data comes in and you have a machine learning process, and the result of this is this model, this network. This network is one way interacting with the human. If you say, oh, this is my decision, you take it, right? So the human are given the task and they are tasked with to do something, for example, making decision whether I should go after this suspect because AI say so. Should I put him in jail, right? So human does not know what to do. So explainable AI says that if many tasks in military, humans are tasked to do some job, for example, identify a target, will you shoot or not, right? So you need to basically have a two-way communication with the AI, and there needs to be some interface here that allows it to happen. Because you want to understand why not, and then when you succeed, when you fail, and when you can trust the AI. It's actually very relevant to these days because this is just last year. If you follow the news in Detroit, in Michigan, and many other cities and states, police using CCTV plus the AI Face ID, that many cases, they went after the wrong people and then unfortunately put them in jail. This unfortunately happened to a lot of African Americans. AI is also many times they think that the congressmen are like similar to mugshot people and they identify them as prisoners. This is very, very worrisome because technology here is not getting any away anytime soon. And we are just using them more and more. We're just getting into this bubble more and more. So in this talk, I hope to convince you on one story, that is, you need to care about robustness, and second, you need to care about explainability. The beautiful thing of these two properties is that they are actually strongly intertwined. Robustness, it gives rise to explainability, and explainability also gives rise to robustness. Okay. And here are my short description of these two words. What I mean by giving rise is that if you do research in robustness, you will tend to generate insights that are also useful for the explainability research. The second point is that if you build AIs that are robust, that work well in both normal and edge cases, this particular AI, if you take it and try to understand, you also will see that it's very likely that this guy is also much more explainable than the guy that does not generalize, that does not work well. We have two things. Similarly, with explainability, if you do research in the XAI, you will tend to generate insight that someone else can go improve the model because, oh, I find the problems here. And then you can give it to some other researchers so that they can improve it. You can inform this AI robust community. And also another property here, the is here should be like tend to. So more explainable AI tend to be more robust by default. I will tell you why. But in the short term, a short argument is that if you can explain what you are thinking well, right? Chances that you are already figure out the pattern, the key, the solution to the problem, right? So that you can work well on other edge cases. These two are very, very hand-in-hand topics. So first is explainability give rise to robustness. Any questions so far? Yes.
So in the example of the school bus, how did you solve it? Did you augment the data or school bus in different orientation, or you solve it in another way?
So we try augment the simplest thing, and then also the approach that everyone tries is to add, just rotate the school bus more, right? Add them to the data set. So that works very well with that particular school bus. However, if you have a white school bus, I went to OpenAI, I saw white school bus, or school bus with a butterfly on it, not the black and white, black and yellow stripes anymore. So it will fail. We try other texture of the school bus, more will fail again. So it seems like that's problem. It does not generalize well enough to other edge cases. Yeah. There's no solution right now other than using like a sensor fusion. You need to use like LiDAR, radar, and other modality, then sense them, fuse them. That increase the robustness. Plus, they're training on more edge cases. Any other questions? Yes.
You elaborate on how we price to the explainability.
Yes, that's the second part of the talk. So first part is explainability goes to robustness. Okay. So let me tell you some story about the previous prior work. The deep learning typically are very successful in the image domain, right? This is a territory of deep learning where people usually throw very deep networks to it, and it typically reduces the error rate really, really low to the point where it's even lower than the human error rate. Human is around 5, and then the model gets now 3%. However, we actually do not know what's going on inside this network. What do this neuron actually encode? So we can actually borrow from neuroscience, Huber and Wiesel, who are the Nobel Prize winners in '54 for their work here that paved the way to our understanding of human visual cortex. The hierarchies in the visual cortex here. So they actually put a cat inside the room and then try to stabilize the cat and let the cat look at stimuli. And they put electrodes into this cat's brain and then monitor the electrical signals. Okay. And they show these cats very, very different patterns, and they found that, oh, there's the neurons at the early layer that fires for edges with different orientations. And later on, this paved the way for later understanding that there are more complex cells that uses these features to understand like shapes and then more complex objects. This study, it turns out, also happened to humans. 2005, Kira et al. Found that they put electrode inside the human's brain and try to measure and then show this person different stimuli, right? Magazines and text. And they found that there is one neuron that consistently fire for Halle Berry images. And also it fires, the same neuron also fires for cat women pictures, which is the role that Halle Berry is very famous for. The interesting thing is that even if the doctor prints out the word Halle Berry in text and show it to him, this neuron also fired. That gives rise to the conjecture that there is this idea of localist neurons or grandmother cell neuron, where there's one neuron that capture like one single entity, like grandmothers or Halle Berry in this case. However, in the computational brains, artificial neural networks, we can repeat this process for any neurons we want. Hidden neurons and a group of layer neurons for the entire network. One approach is that you can gather the data set and then show it to the network and then monitor the response, right? Very typical. However, the problem is that your interpretation may be limited by the data set. This is the research we did like around 8 years ago, where we built the first tool, it didn't exist before that, where it allows humans to visualize the response of neurons inside the ConvNet. In this case, it's a Conv5. Although nobody instruct the neurons, the networks what to learn in this giant like 60 million parameters network, 500K neurons. Actually, there are neurons that arise with very interpretable semantics. For example, there's this neuron that track human faces. And if you go watch this video, there are neurons that actually track shirt wrinkles and even detect text at that point already, not even until now where you have clips. This is all AlexNet in 2012. However, this is very interactive. You can play with it and figure out what's going on, but you will exhaust very quickly what you can try because you want to have a process that is automatically figure out all possible things, right? That this neuron cares about. How do you do it? Maybe one way is to train a generator network, an in-painter, some sort of a data generating mechanism. The way we do it is we follow this second approach where you paint images and then feed it to the network and then measure its response. And you keep going back and forth and figure out what this neuron actually is capturing. So first you take here's a ConvNet, AlexNet, we have 5 convolutional neural layers and then 3 fully connected. And then after you train them, they perform well on the test set. You freeze the weight, then you start from an input image, first you randomize and then push it through a network, right? All the way until the neurons that you care about, then measure the activity. And now you will set the gradients to be 1 to maximize it, and then back propagates all the way to the network. This problem is called activation maximization, or another word for feature validation. Okay, and then so you start from a random image, you push it to the network, up to the layers that you care about, and then from here, you set the gradients and back propagate. What you do here is you generate an image such that you can add it to the original image, update it, right? So this is your difference image. This is original. After you add it together with some multiplier hidden here, you have a new image. If you repeat this process like 20 times, what would happen? Any guess?
It's more accurate.
Right?
It gets more accurate.
You freeze the network, you do not change the network, you just manipulate the image, right?
You convert to a real image.
Yes, exactly. So we hope that because the model has seen these kind of real images, like bell pepper. However, if you repeat this process for the bell pepper neuron, it turns out that, like Zhang said, it actually ended up with very unrealistic bell pepper. You don't know what this image actually represents. Right. However, if you push this back into the network, you will output almost near certainty confident 100% bell pepper. This one, and then very likely even higher than the real images. That's crazy, and that's what my very first paper in a PhD in CVPR 2015, where we document this phenomenon is called rubbish images or fooling images. where we can, just using that process alone, you can generate images that maximize the model confidence, thinking that this is some familiar objects. Actually, right before us, concurrently at Google, Christian Shaggy, who is a mathematician converted into deep learning researcher, he also did something very similar. He started from a real image of a school bus, and he tried to find the small changes that you can add to this real image that converts the network label into something else. And you push this back into the network automatically. This is bell pepper. Instead of starting from a random like us, he started from a real. It turns out that this is very successful approach, and it paved the way for the entire next decade of research on adversarial examples, where the whole goal is to find observations such that you can add it to the original image that change the model prediction. The crazy thing is that you don't even care about the actual magnitude of the pixels here. All you care about whether it is +1 or -1. You just need the sign alone. Then you can march in that direction of the signs. You don't care about the magnitude at all. And you can dictate this, how big of a step you march, and then just add it to the image. That's enough to already change this image labels into something else. Yes, so this paved the way to the entire adversarial machine learning decade of research, and many, many papers since 2013. So that's one story for how explainability, just a very simple test in the wet lab that can inform the entire decade of AI research on robustness, right? People figure out this giant holes, like security vulnerability inside this giant neural networks. That to the 20K papers. This arrow. Now, we can also do a bit more, right? If you interpret the classifier as a graphical model here that maps images to classes, right? So we have the classifier, which is a py given x. What we are doing with this approach is that we are sampling from the distribution of images and labels. However, we do not have this p of x at all. We don't have the prior over images. We only have the classifier. And how come we still sample images? How can we generate images using the previous process? So one interpretation is that we're actually sampling from this energy-based model, where the prior is a uniform prior. We say that any image is equally probable probabilistically, and then we sample from this joint model, and then we got this image. That's how we got this image. The most contribution comes from the classifier. So there are many research, mine also colleagues in the community. Was focused on how can you make the visualization more interpretable, like something humans can understand, because this is great the first time you found it, but then what can you do with it, right? We want to make images not only highly activating the neuron response, but also more realistic, human, so that we can understand and then interpret. And also we want images to be diverse, so you can see many corner, many edge cases, not just one. Right? So a series of bunch of work in my PhD research is on improving this procedure, like the generation process, where you start from a very blurry and then underinterpretable images like this, all the way to realistically looking images. Thanks to the GAN. This is all before stable diffusion. But let me tell you about the latest work. This is probably still the state of the art. I have never seen anyone using stable diffusion for this kind of work. You could try if you want. Talk to me after. So the way it works is that we take the image, push it to the network. So this is your convnet. You want to study, you want to interpret, for example, this neuron. Right? We train a generator. The generator is like a convnet, but upside down, where it maps a small vector into a large image. But if you train this guy well, you can actually form a new model here. So this model maps 4,000 numbers, for example, or 1,000 up to the configuration. do some feature here, and you just do forward and backward, search for a code vector here that maps to an image such that if you push this image through the network, it will highly activate your current neuron of interest. Now, if you run gradient descent again, forward, backward, 200 times, what do you get? It turns out that if you have these three terms in your MCMC sampling, to encourage realism, to encourage class specificity and diversity, you can actually traverse the dream space, the neural space of this neuron, of this network, and then figure out, oh, these are all kind of June code that this neuron cares about. Long beak, short beak, fat or skinny or different colors. So basically, we're traveling the space. So imagine that. What happens if you can do this to human? Actually, there's research right now is doing this to human. We are one of the first people to do this with the neural network that paved the way for other applications on humans. So exactly, if you plot every frames, it looks like this. You can slowly traverse this manifold of words, or specifically the neural activities. And it was 2016 where for the first time, we can so vividly, descriptively describe what is being captured by some certain neuron. Like this is swimming trunk, the model cares about swimming trunk that are blue, and then lipstick that are pink, and then the brambling of this color. Without reverse engineering, you actually do not know what information is being captured at this neuron by this network. It was Java with fiber, and then same for other classes in ImageNet. You can see candles, pool table, and so on. And when you compare them with real images, so these are the real images, the highest activating the neuron, you actually find very similar patterns. It seems like the reconstructed, the generated images are highly matching the real images. Right? This is fascinating because for the first time, someone can reverse engineer what's going on inside these giant neural networks, like 500,000 neurons, which is small at that time. Nice thing about this framework is that you do not need to stick to a single network. You can change it. You can just keep the generator. Want to do it now, use stable diffusion, but plug in any networks that you want to reverse engineer its process. Let's say we did here MIT places. It turns out that it also works. You can reconstruct alley from just these artificial brains, hotel room, pavilions, shop front, residential areas. This is like incredible. It was covering all, it was being covered on a lot of news, MIT paper reviews and media outlets. But we pause and ponder why it can actually generate this, because nobody actually instructed it to do it. This is just the communication between the generator and the classifier alone, and gives rise to these images. So it turns out that one hypothesis is that because the generator has been trained on ImageNet, and basically it has been trained to generate like Junko on blue sky, a mobile home with a background, and then soccer ball with the grass. It knows how to paint these elements. By pair it up with the classifier can provide the gradient, the signals to the generator for how it can put together a coherent residential area picture. This is completely zero-shot generation, completely. Nobody has taught it to do it. There's no such class in ImageNet. Now we also can do something, push a bit more on the zero-shot generation. Like if you ask the model to generate castle, okay, you get something like castle. If you ask it to generate candles, you get something like that. What if you ask it to generate both castle and candle at the same time, right? We got castle on fire. You ask it to generate apron, okay, something you wear when you cook, or brambling, that's fine. But what if you ask you to generate both at the same time? You can get something really plausible, like a brambling on printed on the apron, not the other way around, because that is low. You can basically replace this small network. If you go home today, you could try this by anything, and then start figuring out what's going on with the network. The one bug we actually found from the model put out by Berkeley at that time was that we repeat the same process, but now the MIT places is an image captioner. Image captioner is the model that take the image and then generate a text, a sentence describing the image. If you repeat this process, we're trying to figure out is there any problem with the captioner. What we did is we take this image, right, and we try to. If you push it to the image captioner, it works very well. A bird sitting on a branch, perfect. Okay. Nothing is wrong. However, if you try to fix the output to be a bird sitting on a branch and trying to go back and synthesize the image, thanks to the generator, we actually get these just the trees, just the branches, leaves, no birds at all. So where are the birds? Any idea?
Just you check out the concepts from the captions.
So we search in the code space, a feature space, such that you can generate an image that maximizes the probability of this sentence, right? So back and forth, but we never get the birds. But the model confidently thinks this is these images capturing a bird sitting on a branch. It turns out that I went back and take this image and then remove this bird using Photoshop and then put it back with some similar content patch match, and then push it back to the image captioner. It turns out that the model does not care whether there's a bird or not. It will also spit out like a parrot, a bird perched on a branch in a tree. So somehow the model learns this bias from the text, right? That's our conjecture. It actually ignores the image. If you take my machine learning course, WX plus B, right? So this thing must come from the B, because the bird does not exist in the X. So the bias is independent of the input image. For the first time, we can use this tool, activation maximization, to discover a bug in one of the state-of-the-art image captioner. The thing is, if you repeat this process for the latest model, like blip, you can find very similar pattern. Really interesting. The problem has not gone away, even for the latest 2022-3 model. What else can we do is with this procedure, right? For one network, we also repeat this process. It has been trained to the image classification. So one day after we train it well, performs well on a test set, and we try to synthesize images that these neurons care about. So the beer bottle, mailbag, tennis ball, and so on. Do you realize what's going on with these images? What is the odd thing about these images? Yes, the color space is somehow off, right? It turns out that these images are not RGB, and it informs us that we went back into the procedure, the Python code, and it turns out that there's one line of code that shuffle the channels. Now the model see BGR instead of RGB. It does not matter to the AI because the AI does not care. The humans actually put the semantics on the color, so we actually interpret it differently. So we found a bug thanks to this image synthesis process. That all the training images has been color altered. But without the synthesis, you can never discover this because the accuracy is high. But who knows when you apply to the edge cases, right? It may break. So we talk about explainability, like feature visualization, activation, maximization, or plotting the activation inside the DBS toolbox can inform the robustness. And also the other way, the robust also gives rise to explainability. So this procedure we talk about, this is how you can generate the images that maximize any neurons that you care about. Maximize this activation. The model will think this is bell pepper. You can choose any class you want. It's very easy. it turns out that people use this image. One way to do, like Tim suggested, is that take this misclassified image, right? This is a panda, but misclassified into gibbon. You take these images, put in a training set of the AI, and then maybe you can teach it again to make the AI stronger, right? So that's exactly adversarial training. After you generate this, you put it to the network. Now you say, this is not a gibbon. This is a panda. You compute the error between gibbon and panda, and then back propagate. So if you keep training like this, adversarial training is very simple. It says that you first add a slightly noise to the image, okay? Add random noise, Gaussian noise, and then step in the wrong direction. Let's say given direction. And then clip the perturbation so that it's not too large. If too large, it's obvious. And then you update the network. So back propagate, update the network so that it correctly classifies this image. You repeat this process, it is fast FGSM. You can train the model and make it perform much better than the model before. This is work by AG in our group. So we found that, for example, here, if you train the model regularly on just the real data, it performs well, but it does not work on the edge cases. Adversarial. I told you, edge cases, 0. But if you train with adversarial training, you can dramatically boost this very close to the real image accuracy, 77, 73. So it turns out that adversarial training can give rise to, explainably give rise to the robustness, right? It performs much better. Before it was like very low on the, for example, foggy images. Now it's much better. On contrast images, now it's much better. Okay, so the part 2 of the talk, I want to convince you that the more robust AI can also be, or tend to be also more explainable. So we will use a tool called feature attribution maps. The idea is the following. You have an input image, you feed it to a classifier. The classifier says this is 54% matchstick. Okay, so we will construct an attribution map, which hypothetically looks like this. So in this heat map, it will tell you that, oh, this claim caused the model to think this is a matchstick, and there's no other pixel that contribute against this matchstick decision. And then the white here do not contribute to the prediction. So from this mask, you can, if it's correctly constructed, you can go and tell, oh, this claim is the reason that this model thinks this whole image is a matchstick. Okay, sounds good. It's very important in, for example, an X-ray scan. You want to know if the model thinks this patient has cancer. Where do you see the problem? So one way to generate this heat map is to use first order gradient. Just forward and backward. This is the same process as you train the model. However, you do not update the weights. You just push all the way to the image, and you get this image. You repeat the process. So find the gradients image for the goblet class given this image. We get this. What problems do you see? These images are noisy. You use them as like a guidelines for the humans to tell where the model is caring about, putting attention to. You cannot tell from this noisy image. Same with this matchstick image. It's very, very noisy. So the way to interpret it is that if you look at the high intensity pixels here, these are the pixels that tell you that small change at this location, even the background, can cause large change in the probability of a network, the output of the goblet or hammerhead shark. Right, so these are the problematics, or these are the blind spot, the weaknesses areas of the model, highest sensitivity areas. But they appear pretty randomly, not even around the main object. So what it suggests is that the models are very brittle. You can tune or like any of these knobs anywhere, and you can change the model prediction. This guy probably does not know what a goblet is, probably. how come changing a small pixel can change the entire decision? Right. So our research shows that if you repeat adversarial training, teach the model on adversarial data, actually you reduce the space of sensitivity pixels down. Right. So now the gradients, if you repeat the process, only the highest intensity or high sensitivity pixels are around the main objects, What it tells us that if you now modify this background, it does not change the model prediction. Now it's robust. So what does it tell you? Basically, I need to move faster. Basically, it tells us that if you train the AIs that are more robust, also can interpret it better, because it has figured out the pattern, the mechanism, the rules to classify like words by looking at actually the content here, not the outside in the background. Okay, so the third question is that can we build AI that are both trustworthy, both robust and explainable? That's really the goal, right? The ultimate goal. You want both of these. You don't want to think about the trade-off. Especially when in high-stake decision, when you have to put someone into the jail, when you have to make fatal decision, someone has a cancer or not before you make the treatment call, right? It's really important. You want the model to be accurate and also explainable to you. So the idea is follow Thinking Fast, Slow by Daniel. So we want to build a system 2 model. First needs to explain and then decide. From here is anti-hoc. And we want to build models that can harness external knowledge base, make informed decisions. So you don't want the model to just use the weights itself. You want to input also the knowledge base and the whole thing around decisions of the AI. It looks something like this. Face ID, it's the perfect example for this architecture, where the query image comes in, and then you want the police will use the AI decision and say, oh, the machine will compare the query with the gallery images, and then it will output, this is the person you should go after. Police just take a decision. They cannot scan million images in the US, right? So they must follow the AI decision. This is extremely hard problem because it's 0 shot and then fine grain, because humans are so similar, and there are many people not in your data set. And then people age, they put on makeups, they wear glasses, many cases where there are edges. So we found that if you put glasses on, the existing model can still retrieve this person out of 1,000 people. These are the top 5. So you can see the correct person is retrieved given this input image. So it performs really well, near perfect. However, in the COVID areas, people put on masks. Suddenly, the model drop accuracy to around 39. Right, so the person, this female person is gone from top 5. So with more explainable method and also more robust, we actually are able to push this person back to the top 5. So you get 10 points improvement without any retraining the model. So the idea here is we improve also the accuracy. That's number 1. And second, we produce explanation here that the model is using this forehead region to make prediction, not any other regions, especially the black one. Here we show the weights of each patches that the model uses. The black are not used. Here you can see how the model makes the decision. If it does not make sense, the police can discard the prediction. I will skip this due to the time. But the idea is that now the model works really well without even retraining. The idea is that you would compare patches and allow the AI to select the patches by itself using optimal transport that can maximize the prediction. That's the idea. And now the model would work with mask and sunglasses and even faces in different orientation. better than before. First, still far from perfect, but better than before. You can see it almost improved for every single condition we tested. This is a work by Zhang and Mohammed at Nurse 22. So the idea is that we also can use this patch-based decision-making process because they are one, more robust, more trustworthy. Second, they are more explainable. For example, you compare patch-wise, you will see normally the model would think this image is a parachute image, right? Because mostly because the dominant pixels here are clouds, blue sky. However, the model, if you allow it to zoom in, it actually figure out this is an ibex because it compare only a few patches here and then figure out this is actually similar to ibex the most. Here in the adversarial case, if you add a patch that looks like a toaster, the normal model will take the whole image and then think that this is a toaster because it has been fooled by just small changes. However, if you let a model to fine-tune its attention, it can now select the most discriminative region that is similar to the training set. Because now you ground them to the training set of chickens. You actually find that toaster never appear in my training set, but chickens appear. So now I compare them and then the model thinks this is a hen. It also improves our accuracy in the edge cases on many tests. I will tell you one case where it helps human accuracy as well. For example, in bird classification is extremely hard because many birds are similar and you have to use different cues like sizes, colors, habitat, and shape to make prediction. That's usually the human expert do. If you ask human this image, what is choose one among two types? It's nearly impossible for the lay user who are trained to do this. It's too hard. It typically is, however, we change the problem to given this input image, we push it to the AI, and AI will give you the prediction. Could be correct or wrong. Nobody knows in the test time. However, we support this prediction with some explanation. And then now we ask the model to think, do you agree with American goldfinch or not? Now it reduces the decision-making space to only binary for human and make it much easier. Plus you provide some evidence from the AI, right? And so on. So it turns out that in this approach, if you provide not only the image, but not only the prediction, the image, but also how the model ground this to the training set, like this, it actually helps improve user decision. Like here from 69 to 67 to 69 with explanation. When you provide them explanation, it's much better than without. To conclude, I want to, in the last 2 minutes, I want to tell you my future of the AI. What should they look like? So right now, if you do GPT-4, Stable Diffusion, all of them are like this giant black box. You give text input, you text output, that's all. This is a big black box. Again, I tell you at the beginning of the talk, this black box tell you when you should breathe, how you should breathe, what facts appear on Google, right? Who you should reproduce with, right? What you should purchase. This is all this black box is telling you what to do. And humans try their best to do what they call post hoc interpretability. Try to extract something out from here or from here, but it's one way, and it's up to their subjective call. So it's really problematic. The future of AI should be bottleneck XAI. And to put this out soon. So it should be two-way communication. So it's okay. You cannot get away completely from black boxes. I can have two black boxes here, but there must be a bottleneck here. I can afford two-way communication, right? The human must first able to understand. So that's that way, this way. human must be able to debug and audit, just like how human audit each other, right? Finance, tax, and so on. Why can you not audit AIs? The third one, you must be able to do the other way. You need to influence their decision, change their decision, edit them in a way that human can do it. It's not like just the optimizers only do it, right? How can you build bottleneck XAI? That should be the future. That should be the future. And thank you very much.
Okay, are there any questions?
Yes.
Can you explain again this generator that you use in the middle of the.
Yes.
This part.
I remove some part of how we make this happen. Basically, for now you can train a generator. It is the one that is reversed. So instead of classifying, you make the other way. So you have a vector that maps it to an input image. You can use now VQGAN, state of the art, or stable diffusion. You plug it in here. Now this whole thing becomes a single network. You search in a space of like 5, 12 numbers to use optimizer the gradient descent, such that when you push it through a network, it will give you some image you don't know, but you don't care. But you push it again to this giant black box, the black box will output something. If you forward pass, backward, update that guy, forward, backward, forward, backward. So until this number goes high, then you stop the procedure. It turns out that if you repeat the process, you can get the really realistic looking images.
But what is the meaning of code over there?
Just a feature of
Okay.
the vector. Embedding.
Oh, embedding coding.
Just a vector of real numbers. Yes.
I have a question with bottleneck AI. If you can go back to your last slide. I guess the first question is how do we combat user fatigue? Right. So I think that user fatigue. Yeah. So bottleneck fatigue or whatever you want to call it. And then the next thing is when you're looking at is that bottleneck, that human in the loop, could it be several humans in the loop? So one is how do we combat fatigue? And in this, could you have more than one human in the loop?
Right. So the user fatigue is that you mean that they're having to communicate too much, right?
Yes.
And then at some point they don't want to communicate anymore, right?
Yes.
Here.
Yes.
That's a great point. But remember, if you have to audit like an accident of Tesla, if you have to check if person should be arrested, person should be 5 years in prison, right?
Mhm.
There's no way around the fatigue, right?
Right.
You must communicate with the AI because there's no other way. The phone, you can choose to turn it off. Then when it comes to legal and actual society matters, it's hard to turn off. But yeah, how do you, I think it's open problem. At least now we want to first build a prototype that establish this. Then I think the next step is to think about how you can better improve it, like reducing fatigue. Yeah, that's a very good point. I also have not thought of like, what if there's a crowd here? Honestly, but that's some very good question for the future researchers, students. Yeah, maybe you can have a crowd here that can together, edit this model. I think this could be happening if you make GPT-4, for example, a bottleneck. Right. So many people are interested in playing with this and then edit them. But so far, all they can do is edit the inputs. Yeah. Yes.
So I was sort of thinking if I were to go home right now and fire up Stable Diffusion and just start cranking out images and run them through some kind of classifying system, would it be a potentially good idea to, rather than just randomly trying noise, would it be a good idea to try some kind of prompt-based image generation system that can produce like an initial image, then use that.
Start from real versus start from random, right? The first stable diffusion is a generator, not a classifier.
Yeah.
So you can start from the real, but it's better, but it can basically give you a prior over where you want to search. If the real is near your target, then it's better. Otherwise, it could be a bias against you. Does it answer your question?
That might be something.
But most people just start from random. It actually works. You don't need, because the process is really easy. It's just stable diffusion, need this GPU to run. Yeah.
So I have a question related to the attack pattern, which can be applied to image to like mislead classifier. So I'm particularly interested. So like there are like majority, which is like service which you can find like keywords to generate images, and there are like artists who don't want their artwork to be like in the learning data set, and then there are like research groups who provide like any pattern they can apply in their artwork to like confuse the learning model. Do you think like this, so the artworks that apply with that attack pattern can use to improve the like image classifier models, like even though they are like intentionally like applied with like attack pattern?
Do you mean how to, or do you suggest a proposal?
So I mean, that's the like fact that people are trying to confuse the image classifier using attack patterns will result in the improvement of the image classifier model. Eventually, I mean.
Eventually, yes, because this is a typical security, right? It's an arms race. If the attacker becomes better, the defender will try to be better. They keep going, and actually they help each other. Without one side, the other cannot improve. But how much damage one side caused to the other? That's the consequence at that time.
This question comes from Ari Ryan, and he says, for this interface to work well, won't we also need an intuitive natural language-based interactive interface for the debug and audit process?
Right, exactly. So I agree with Harry that the reason I came to NLP like 3 years ago, switched to part of my efforts with NLP is because I believe in this bottleneck needs to have the language. Language is very, very important communication vehicle. And it should be part of the equation, not just images alone. If you, for example, scan documents and try to predict, financial decision, right? Or any court decision from huge piles of documents, you need text. You also need text in the images as well, because text can summarize very well, rather than showing a lot of pixels and humans don't know how to interpret. But all of this is very general plot. It depends on the actual application. If you want to look at the application, for example, I have something I can show. For example, in birds, we show here this is part of the future work, but we only build the interface at the moment. Any undergrad student or master student want to join, you're welcome to. So the idea here is you let the AIs to figure out what feature, the actual feature in the bottleneck, not the input, that the model can use to make prediction. So if you choose, for example, these 3 patches, the model will incorrectly map it to this bird because you can see they also all red birds, right? However, the moment you ask the model, hey, can you also consider the beak? Now the model retrieve the correct cardinal. So this is to show that if a human can interact with the AI, right? In this case, there's no text. I can imagine text can, for example, annotate when you see the beak. You can help a human tremendously. Other questions?
Any other questions? Okay, thank you.